What specific problem does FocusLLM aim to solve, particularly in terms of the limitations faced by existing large language models when processing long texts?
FocusLLM aims to address the significant limitations of existing large language models, LLMs, in processing long texts, particularly the computational complexity and poor extrapolation performance associated with traditional transformer architectures. Specifically, it tackles the quadratic growth in computational demands as sequence lengths increase, which makes training on longer inputs prohibitively expensive. Additionally, FocusLLM mitigates the issue of information loss from earlier parts of the text that occurs in many context scaling methods, which hampers tasks requiring precise understanding, such as information verification and question answering. By employing parallel decoding and maintaining low perplexity on long texts, FocusLLM enables effective comprehension and reasoning over extremely long sequences, achieving a context length expansion of up to 400K tokens while using significantly fewer training resources. This innovative approach allows FocusLLM to retain the generalization capabilities of the original model while enhancing its performance on downstream tasks involving long context documents.
How does the proposed FocusLLM algorithm work? Please illustrate the methodology step by step, detailing any unique components or techniques introduced.
The proposed FocusLLM algorithm operates through a series of innovative steps designed to enhance the processing of long context documents. First, it segments long sequences into manageable chunks, ensuring that each chunk does not exceed the model's default context length. This segmentation allows for parallel decoding, where candidate tokens are generated simultaneously from each chunk, rather than encoding the entire context into memory, which is a common limitation in previous models. Unique to FocusLLM is the introduction of a small set of trainable parameters that augment the original frozen model, enabling it to aggregate information from these parallel decodings effectively. Additionally, the methodology incorporates local context injection, where a limited number of local tokens are appended to each chunk, allowing the model to focus on relevant content while maintaining global information necessary for accurate decoding. This combination of techniques results in a training-efficient framework that can handle extremely long sequences while preserving comprehension and reasoning capabilities.
Can you explain the parallel decoding process in FocusLLM? How does it differ from traditional encoding methods within transformer architectures?
The parallel decoding process in FocusLLM involves the simultaneous generation of candidate tokens from different chunks of a long sequence, followed by aggregating these tokens to produce the final output. Each chunk is processed independently, allowing the model to focus on relevant segments of the text while maintaining global information necessary for accurate decoding. This contrasts with traditional encoding methods, which typically involve transforming text segments into hidden states for later use, often retaining key-value caches for subsequent processing. In FocusLLM, the emphasis is on generating the next token based on the current chunk rather than encoding the entire context, which allows for more efficient handling of long sequences. This approach not only reduces computational complexity, but also mitigates the information loss associated with earlier context, a common issue in traditional methods.
What is the significance of the loss functions, continuation loss and repetition loss, used in training FocusLLM? How do they contribute to the model's ability to recover global information?
The loss functions used in training FocusLLM, specifically continuation loss and repetition loss, play a crucial role in enhancing the model's performance on tasks that require understanding and generating long sequences. Continuation loss trains the model to predict the next token based on the last local tokens, which helps it generate coherent continuations of text, thereby improving its language modeling capabilities. On the other hand, repetition loss focuses on ensuring that the model can accurately restate information from the preceding context, which is vital for tasks that depend heavily on context retention. The combination of these two loss functions is essential. While continuation loss enables effective generation of new tokens, repetition loss ensures that the model can recover and utilize global information from earlier parts of the text. This dual approach allows FocusLLM to maintain a balance between generating new content and accurately reflecting the context, thereby enhancing its overall understanding and reasoning capabilities on long sequences.
What results were achieved with FocusLLM on the long bench and infinity bench tasks? Discuss the performance in relation to baseline models.
FocusLLM outperformed all baseline models on both the long bench and INFTY bench tasks, demonstrating its capability for effective understanding and reasoning over long sequences. Specifically, it achieved the best results on long bench, which evaluates a variety of tasks, and on INFTY bench, designed for extremely long contexts. In contrast, baseline models, particularly those employing sliding window or condensing techniques like streaming LLM and activation beacon, exhibited significant performance drops, with some tasks nearing zero effectiveness due to their inability to maintain precise understanding of the full context. Additionally, fine-tuned models, such as LongChat and CEP, struggled with lengths beyond 128K, highlighting the limitations of their context handling. Overall, FocusLLM's performance across these benchmarks underscores its superior efficiency and effectiveness in processing long sequences compared to existing models.
What are the limitations or potential drawbacks of FocusLLM as mentioned in the paper, and how might these impact its application in real-world scenarios?
The paper identifies several limitations of FocusLLM that could impact its real-world applications. Firstly, while FocusLLM maintains low perplexity and performs well on downstream tasks, it still relies on a limited number of trainable parameters, which may restrict its adaptability to highly specialized tasks requiring extensive fine-tuning. Secondly, the model's performance can vary with different chunk sizes, and while larger chunks are generally preferable, they may not consistently yield better results, indicating a potential trade-off in processing efficiency. Additionally, the model's reliance on both continuation loss and repetition loss for training suggests that it may struggle with tasks that require a balance between generating new content and accurately recalling previous context, which could hinder its effectiveness in complex scenarios. Lastly, the computational complexity, although reduced, still poses challenges when scaling to extremely long sequences, potentially leading to increased inference times and memory usage in practical applications.